Swayam Prabha. Digital India. Educated India.
Good morning. Welcome you all to this lecture in this particular course on analytical, spectral and microscopy applications of inorganic complexes and nanomolecular systems. In the past two classes we have two classes we have already built enough base for this particular EPR spectroscopy, and now let us continue with it. Particularly we have seen in the previous class how the EPR pattern signatures come on this in terms of the electron nuclear coupling and electron coupling, and these signature patterns are a bit disturbed by another parameter called the anisotropy, and I draw your attention onto this particular slide now. So that means the anisotropy means the G does not have one single value like isotropic, it will have more than one value. It can be 2, it can be 3, a maximum of 3, that Gx, Gy, Gz, or 2, that means any two of them are equal, the other one is unequal. So now look at the case of the anisotropy. What we are saying is that if you look at Gx is the Gy and the Gz, if all these three are equal, it is called G iso or isotropic, and you get a system with the distribution of these electron being the spherical kind. Now any two of them, let us say Gx, Gy is same but less than Gz, then you will get, and along the z axis you get a elongation kind of thing, and the other way you can get as well. So this is one of the axial, one axis along the z axis. So or Gx is equal to Gy and greater than Gz, then you will get oblate kind of thing, again another axial. Okay, so these are called the axial kind of a elongations. So that means an asymmetry is there. And the third category is, the last category is Gx is not equal to Gy, which is not equal to Gz. So that means all three are independent, and then you have a kind of a system of this kind. So this is what is rhombic. So you can have isotropic, spherical, axial, either in the direction of this or the other way, and then rhombic type. So these are the factors which distorts the spectrum, which otherwise would have looked very nice, very bright kind of a thing with all the signature patterns. Now what are those? Now look at, when you have a isotropic, straight away you get one absorption nicely and one derivative curl. And when you have Gx, Gy, Gx is equal to Gy and less than Gz, you can see that one small blob and one bigger blob you are getting here, okay, and in this. And in the other way, Gx is equal to Gy but greater than Gz, reverse way, okay. So that means you have the lower G coming here, the upper G here, and that is equal to G parallel, and this is the G perpendicular. Now here this is the G perpendicular and this is the G parallel, which you refer with respect to perpendicular with respect to the magnetic field and parallel to the magnetic field. So the orientation of your molecular system with respect to that, what you refer to. And in case of the rhombic, which is Gx not equal to Gy, not equal to Gz, so you will get all three signals. Now your distortions add this kind of a features. So instead of one, you will get two with one small, one big, one broad, one sharp, one resolved, one unresolved, these kind of things that you will find, or three of them, so that will be for rhombic. So this is the kind of thing. So same thing I have put here on the right top here, please have a look at it. Gx comma Gy, there is nothing but the perpendicular, and Gz is nothing but the parallel. You can see very small blob, okay, and if you take this one, you can get all this. Now these are axial symmetry. Then when you have rhombic symmetry, you would get one here, another here, another here. This is from absorption spectrum, this is from derivative spectrum. Okay, here also derivative spectrum for these ones, because there are two types of these Gx, Gy is equal to Gy greater than Gz, less than Gz. and those are all the things that are which are shown over there. Okay. Now here you have Gx, Gy, Gz different. Now we got the additional parameter to the EPR spectral domain is called the anisotropy. You already have electron nuclear spin coupling, hyperfine coupling, electron nuclear, other nuclei, nearby nuclei, super hyperfine coupling, and then electron coupling, which is weak one. If it is weakly coupled, then you will get ferromagnetic or antiferromagnetic, or if they are strongly coupled, you will get a zero field splitting kind of thing. And now on that, this anisotropy gets overlaid. Now to understand all this, let us start doing some examples. Let us do an exercise together in the interpretation. So these are all interpretations I will be giving, but please join actively in understanding these things, because everything is involved in this interpretation. This just the spectra will not tell you the things unless you follow what I am talking about, and they are very logically spoken, so therefore it is very easy for you to understand this. Now you have studied in your inorganic chemistry, coordination chemistry, there is something called Jahn-Teller distortion. Most often people understand this by copper D9 spectrum, so that you have 6 electrons in T2G and 3 electrons in the EG, and in an octahedral system, out of the 3 electrons, then 2 are in one and 1 is in another. So that is it can be so that is you have this is in the octahedral, so you have T2G, already 6 electrons are there, and 3 electrons are there here. So it can be either here or it can be in this way. So if you call it dx square minus y square and dz square, so that means your unpaired electron could be either in dz square or in the dx square minus y square. This makes a difference. That is, when the unpaired electron is in dx square minus y square, that means there are 2 electrons in dz square, then you will have a elongation, and the reverse of that will become a shortening of the bonds. This is what you have already studied earlier, and that will reflect in the G values that we have just now looked at, parallel and perpendicular, or x, y and z value. That is where the thing is at. Okay. So whatever I explained already you have seen, and this is the thing where you can have the 1 electron in the x square minus y square, or 2 electrons, 1 electron in the dz square. So this will give a compression, this will give elongation. Just now I have already explained to you. But most examples in the literature you will find elongation, most examples. But for example here this together is octahedral, but there are some ligands which are protruding out, R groups. So these R groups will have a steric, therefore they turn the geometry a bit and get stabilized into the situation where there is one unpaired electron in the z square, not in the x square minus y square. So there you get the shortening. So tetragonal, the shortening kind of a distortion. And now if you look at this particular thing, you can see the corresponding spectrum. This is with the R group being this cyclohexyl. So in the cyclohexyl you get these 4 lines plus this one, and whereas if you put the tertiary group you get exactly the reverse, and this is your G perpendicular and this will be your G parallel, and in this case this is your G parallel and this is your G perpendicular, exactly reverse, because the elongation is becoming the shortening of in these things. So how do one explain the lines of this? So the lines of this is electron, odd electron is in the copper metal and a copper center, because the copper 2 plus, which is D9, this electron belongs to the copper nucleus, and the copper nucleus has got a 3/2. Then what you should get, 2Ni plus 1, 2N 3/2, 2 into 1 into 3/2, that will be 4 lines you will get. So anisotropy tells 2 sets of lines, 1 set, 2 sets. So anisotropy is there, and in each thing 4 lines should be there. You can see 4 here, and the 4 will also be here, but their spacing is so small they got overlapped. So that is where, that means this coupling value of in this direction So, G parallel direction is much smaller as compared to the G perpendicular direction in when you have a cyclohexyl derivative. On the other hand, you will have the reverse of these ones. Okay. So, that is so it is not that it is one single peak, this is also having the 4, but it is not resolved at that frequency that is being used or at that field that is being used, where the separation of the A parallel here in this case versus A perpendicular, and this is what which determines that. So, in this case, so A perpendicular quite large, okay, and then here the A parallel is a smaller. So, therefore, it got merged, make this. So, I hope you understand, and that whether this complex is in the state of the tetragonal distortion or tetragonal compression or elongation, you can find from the EPR without going into the X-ray structure. Otherwise, it can be known only from X-ray. Sometimes even in X-ray structure, if the resolution of the X-ray structure is not very good, the difference in the bond lengths will be somewhat bad, then you will not be able to differentiate whether it is the tetragonal elongation or compression. But here you can easily differentiate. Let us go into another example and try to interpret how this unpaired electron thing. Again, here we have a complex here. Please have a look at on this. So, you have a diphosphine complex 1, other 1, 2, and 1 benzene attached directly with the Fe carbon. The iron 1 system here you have. Okay. This is again you have the anisotropy, and the anisotropy is you can see the intensity is 2, intensity is 1 ratio, 2:1 ratio. That means 2 of them of the directions the G value or A value is similar, and one direction the G value or the A value is different. Now, you can see both of them. So, then you have the G2, G3 are overlapped on the thing. So, you can call one of them as perpendicular, other as a parallel as well you can, but otherwise this is a fitted spectrum, that is why they have shown the G2, G3 kind of a thing. So, it is somewhat rhombic kind of a distortion, but not 100% rhombic type of a distortion. Now, here you can see 1, 2, 3, 4 these 5 lines here and this. So, the iron, if you look back earlier, iron does not couple because its I value is here you can see that the iron has got 57, which is half, but its abundance is very low. So, therefore, you will not expect any coupling coming from the iron nucleus, but in the previous example, yes, there was a coupling. There was a copper I is 3/2 and with a good abundance, absolutely great abundance. So, here you do not expect. So, what will be coupling here? So, what will be coupling here is the phosphorus. Phosphorus is 100% half. So, you have 5 phosphorus if they are equivalent. So, 2 into 5 into half plus 1. So, that is 6 lines you can see, and each of this is split 1, 2, 3, 4, then 5 with very little one or the overlap. So, therefore, these phosphorus nuclei are coupling with that, and you should get similarly there, but you will get for the G2 as well as G3 and then the overlay. So, therefore, you will not have the number of lines as expected, the 5 and the 5 or 6 plus 6, 12 lines you will not find so easily, but there they can be, by computationally you can model and then match with them, and that is what is being done. So, this is your simulated spectrum, this is your originally thing. Now, what additional thing you can see basically here is, if you look at each of these, and you have the axial kind of thing, you have a equatorial, and there is some level of the coupling constant difference. I will not say mismatch, we will say coupling constant difference will be there, okay, and that is where these are the weakly coupled ones. So, you can see that the equatorial 31p are actually inequivalent, and one is more weakly coupled than the remaining ones. So, that is why your number of counting of the lines are not properly coming. So, similarly, they also have different kind of a coupling constant as well. So, the EPR spectrum thus demonstrated unambiguously that the iron 1 complex, this one is what are the features we have seen? The features we have seen are the coupled with the phosphorus. That means this odd electron is not completely residing formally at the iron alone, it is moving to the phosphorus centers as well, and that is what basically you can get information. That means your spin density, that unpaired electron spin density, is not 100% localized, but it is distributed because of the kind of a distorted geometry that you got. It is somewhat close to rhombic, but not 100% rhombic kind of thing. It has a lot of axial, a little bit of rhombic kind of thing. So that is the distortion. So very important. So that we can make so spin density. So from the spin density you can talk about the structural features. Here we can say that the structure is distorted, and this is applied in using some coupling reaction which is written there. You can always study that part of it. Okay, let us look at maybe few other examples. So one of it is the copper spectrum which is shown here for the copper perchlorate. So just a while ago I have already explained about the copper. I don't need to tell you once again that it has the G parallel and G perpendicular. The G parallel is showing all 4 lines because I is equal to 3 over 2, 2 into 1 into 3 over 2 plus 1, the 4 lines you can nicely get. What about the for perpendicular? There should be 4 lines, but their eyes, the A parallel is so small that the lines get overlapped and therefore they get merged. So therefore you have so you can explain that the A parallel is much greater than that of the G parallel, and therefore you can explain the spin density, delocalization aspects, etc. The spin density, how much it spends, and that will help in understanding the covalency factor in the bonding, other things. So you can see hyperfine is always much greater than that of the G perpendicular, resulting in a large splitting of the width only. Now look at another example here, the vanadium, not for the copper. The vanadium case I is equal to 7 over 2, and this is a good abundance. So therefore you can expect the coupling of that. So this is vanadium containing chloroperoxidase in the enzyme, and this is the EPR spectrum taken from the enzyme. Now if you take this one, and this is you can always fit with this. If you work out here 2 into 1 into 7 over 2, there is only one vanadium there in that, so that is 8 lines. So if you look at the spectrum that is obtained here, so it's 1 2 3 4 5, there is one more here, 6 7 8 9 10 11 12 13 14, something like 15 16 are there. So obviously this is not coming from just the one alone, it is coming, if it is one alone you will get 8 or lower but not higher. So here you are predominantly much higher, almost double the number of peaks. So if you see that this, there is a one set, if you try to fit with the giving some different trial and error kind of a parameters, you can fit into 2 spectra. So one is with this 1 2 3 4 5 6 7 8, that is one 8 line spectrum, with another one here under this, one here, then one more below this, one here, one these ones. So these are all coming from one of the type of the vanadium, and this is coming from the another type of the things that you can see. So it can be fitted into 2 sets of the hyperfine coupling. So therefore you will get correspondingly the 2 sets will give 2 types of the values of the A. So one of these you can call as the intensity higher in this G perpendicular, the other one is the G parallel. In the other case you are seeing very separately in copper, you see here these are separate, perpendicular and parallel, but here the perpendicular parallel are overlaid so much, so therefore you need a fitting. So that's where the thing is, and that's because your G parallel values have got much smaller the coupling constant, the A parallel, as compared to that of the perpendicular So that is why you have the structure of the hyperfine overlaid one over the other. Again you have the anisotropy of the axial type of anisotropy in this. So these are all very important for the structural features, bonding features to explain. Look at another example which is from a biological system of this nickel containing, kindly look at the slide, the tetrapyrrole F430 factor, and you have a nickel here and all of these. Now if you reduce, you can reduce this nickel center from 2 plus to 1 plus by various means, and then now look at, these are all 4 nitrogens are coordinated, and then look at the spectrum. The spectrum has come over here, and this is with the natural abundance. Now you can see there is some fine structure and there is another. So therefore you can see the definitely axial anisotropy. So there is one big one, one small one, or 1:2 ratio. Absolutely, 2 of them will have very similar values or very little difference in their values. One of them will have a much different. That's what you would see. And there is some hyperfine, but you don't see very clearly those kind of a features here also. Now of course, if you use the nickel, has got 3/2 just like that of the copper, then you get your 4-line spectrum. And you can also have the nitrogens. So nitrogen will have I is equal to 1. For nitrogen, I is equal to 1. So therefore 2 into 4 into 1 plus 1. So that is 9 lines you should get, and you can see the further splitting coming in each of these things. So here also you can see the further, there are a lot of splitting is there. In order to understand the splitting, because the nickel natural abundance is low, much low, something like 5 or a lower percentage, this has been re-synthesized by using a microbiological bug wherein nickel 61 has been supplemented, and therefore you got the enriched F430 factor. Now you can see the corresponding spectrum. So you can get 1, 2, 3, 4 broad features. That means because of the nickel, and in each broad feature you have a smaller ones, and those smaller ones should come as of 9 lines because of the 4 nitrogens, because nitrogen I value is 1. 2 into 4 into 1 plus 1, 9 lines. So each one of the small one will have a 9 lines here, 9 lines here, 9 lines, but they will overlap. But their further isotropic coupling value will be so small, you will not see each one of them separate. Now here, if you look at here, you can see those things as well. But here already 2 of them are overlaid, because this is coming from the 2 axes and this is coming from only 1 axis, and plus the nitrogen coupling. So that's where you can see that. So it's a very characteristic spectra, nothing else can happen, and so therefore anything can be easily understood by the looking at the spectra. Now you can see the signature patterns which I have been talking about in the past 2 classes, the hyperfine and super hyperfine further splitting. I explained to you all of this using examples. Now you don't need to read all of this. I can tell you that if you look into the biological system, metalloproteins, there are metalloproteins with iron, iron 2, iron 3, nickel, nickel 1, nickel 2, nickel 3, copper 1, copper 2, copper 3. You look at their electronic configurations and look at their the S value. Some of them is 0, that means they will not be EPR active. Some of them is non-zero, they should be EPR active, and some of them half very nicely you can see, and higher values you can see with a lot of distortions and other thing, because you have a strong coupling in those things. If S is equal to 2 means obviously you have a strongly coupled system, because more electrons on the same metal center. So therefore you will have the further splitting. You need to study those at different magnetic fields, then only you will understand. Otherwise, if by taking just one EPR spectrum, a complete understanding will not be there. So those which are non-zero, they are all EPR active, and those which are 0. So for iron 2 plus also there is non-paramagnetic and paramagnetic, iron 3 plus, then nickel 1 plus, nickel 2 plus, one of the system, nickel 3 plus. So you can see in one of the state or the other, these are all EPR active, that you can see in all of them. Okay, so this is the hyperfine with the weakly coupled, strongly coupled, those features will come into picture, and then these one can also look at the G values for the spin orbit kind of a coupling. Spin orbit kind of a coupling for the half filled, less than half filled versus the greater than half filled, because the G value will be greater than G or less than G. So if it is less than half filled, less than G, greater than half filled, greater than G. G is free electron. So those will come into the higher side, these will come into the lower side with respect to the free electron, which I explained to you earlier. So these are mostly. So having seen that, let us look at some example of the iron sulfur proteins. Those we know that there are 2 iron 2 sulfur proteins, 3 iron 3 4 sulfur proteins, 4 iron 4 sulfur proteins, of which those which are shown by the blue lettering, they are the EPR active, because S is equal to half. The other one is S equal to 0, EPR inactive. Then here this is EPR 2, the S is equal to 2, but it is very strongly coupled, you will not see, becomes very broadened, and but this is 3 iron 4 sulfur 1 plus, you will see nicely. So that means oxidized one you can find from the 3 iron, reduced one you will not see a very clear cut kind of a thing, blurred one. So you can say that itself is a 3 iron 3 sulfur 4 sulfur. And similarly 2 iron 2 sulfur, one of them give a good, other will not give. 4 iron 4 sulfur in the reduced form, which is 1 plus, you would see S is equal to half, you get an I spectrum. And if it is oxidized 2 plus, then you will not get. Then high potential iron sulfur protein, the reduced one will not give, but the oxidized one will give S is equal to half. So all those with the S is equal to half will give, S is equal to 0 will not give, S is equal to greater than 1, there's 2, etc. They will have a strongly coupled, so you will get a broad, you may not see very good features in that, unless you go for the variation in the field strength. And so now you can see none of the spectrum matches with the other one. That means these are characteristic, and then you can find whether the given protein has got this kind of iron cluster, this kind of iron cluster, or this kind of iron cluster. So that means your EPR spectroscopy became a tool for identifying that particular one. Let's look at one more example of the thing where an inorganic complex like this. So this is the phenanthralin, and this is the water, and this is a pentacoordinated copper complex, copper 2 plus complex. You can see 2 plus here. This complex is introduced into a DNA helix, DNA double helical structure. So you can see that. Now what is happening? So where is the magnetic, where is your electron spin? Electron spin is in the copper, and in this copper complex basically. So copper and the copper complex. So this whole thing is shown here. This is shown like a cylinder, and your complex is shown like this elliptic. Now the orientation of this particular copper spin, this is we are talking about, with respect to the main field. So this, the copper will show the G parallel and G perpendicular, that we know very well. Okay, G parallel and G perpendicular. So that means the copper molecule is shown by one vector called G parallel, other vector called G perpendicular. Now how this is oriented with respect to the external field, with respect to the ZF, that is what determines your spectrum, and based on the spectrum you can tell how it is sitting inside the double helix. Now let us assume that this one, this particular G parallel is aligns with your Z axis. So and that means the theta value is 0. If the theta value is 0, that means your G parallel aligns with that external magnetic field. In such a case, what you will get, your parallel things get these basically enhanced, and the other angle is the G with respect to the magnetic field, that phi. So you can keep changing the phi at 0 will give the best or maximum signal, phi at 30 will give little lower signal, 60 lower signal, perpendicular much lower signal. So that means you can see that the different orientations of this, and actual spectrum, if you match with this, you can tell how it is oriented in that. It's not only that, you can also keep this perpendicular. So you keep the G parallel perpendicular to this, that theta is 90. Again, if you take the theta is 90, and if you look at all the different phi values, so that is with respect to the field, then 0 will give lowest, then 30 is a little better, 60 a little better, and 90 much better. So this kind of a behavior will explain that the way that your complex is oriented. So this is actually different molecule, this is the double helix is a different molecule, but this compound is put inside that. So as such, DNA doesn't have any paramagnetism, but because of this complex, now you can understand how this complex is interacting with the DNA. So we can also have other ways of this when the G parallel axis is inclined. So now we looked at the 0, we looked at the 90, now you can look at the 45 degree. So if this G parallel is 45 with respect to this axis, then what will happen? You will get a mixture of this behavior and this overlaid on those things. So therefore you get this. So using these kinds of control spectra or predicted spectra, you can get your own spectra for your system, and then match and find out how exactly this particular thing is lodged in your double helix. Now we have seen how isotropic, anisotropic signals coupled with electron nuclear coupling, of the same nucleus, electron nuclear coupling of the neighbor nucleus, all of these we have looked at, and how this gets blurred when you have a electron interactions are very strong, and when the electron interactions are weak, then no problem, then you can see all those. So we have looked at quite a few examples of all these features coming using a transition metal kind of an example, wherein nowhere you will get isotropic spectrum. You get always an isotropic spectrum with a axial type, or very rarely rhombic type. Okay. So we will continue with doing some exercise in the next class by taking different kind of examples and do a kind of the classroom practice and all those things. So look forward for that. It will be a classroom practice wherein we'll have a kind of an interactive kind of a session on that. Thank you very much.